Hi, good afternoon, everyone. It's my great pleasure to introduce our speaker for the CIQM seminar today, Yang Zhang. So Yang got his bachelor degree from Tsinghua University in China and went to Germany for a PhD study. And within 3.5 years, he obtained the PhD from Max Planck Institute at Dresden. He worked on theory and the computational approach to quantum materials, especially focusing on nonlinear optical properties and spin-dependent phenomena. He's an expert, real expert in developing innovative algorithms for calculating material properties. He's a highly sought after theory collaborator by various experimental groups. And in 2019, he joined MIT and completely switched the field to the study of Moiré materials. And that's what he's going to tell us today. Also, I want to mention that Yang's achievement is already recognized by the prestigious Ono Han medal from Germany. So with that, Yang, the floor is yours.
Thank you, Liang, for the very nice introduction. So today I'm mainly talk about the quantum chemistry and the density function theory for the correlated Moiré states. So this is a talk that we are going to map the kind of long periodicity Moiré sublattice with 10,000 atoms to a very simple like diatomic crystal, and then using this simplified picture to describe the low energy dispersion. And so, yeah, let me start. So this talk are based on three work I did with Professor Liang Fu and Hiroki Isobe and Noah Yuan in our group. So, and based on three work on the Heterobilayer TMD and also the homobilayer TMD, and finally on the effective density functional theory, and also very thanks to the experimental collaborators, for example, ATAC and also the Connect group, and also the Columbia group for the many information discussions. And okay, so let me start with a simple comparison of the TBG and the Tuesday TMD. So why we are interested in the TMD, the Tuesday and TMD, and what can they provide? I mean, what kind of phase can we get out of them? So we know that all the correlated physics in the Moiré system became attract our attention since the discovery of the superconductivity in magic angle graphene. So done in 3 years ago in public group. So in the TBG system, so if we look at the no energy kind of effective theory, we know that the no energy dispersion is described by the massless Dirac Fermi in a periodic potential. So, and then, so the difficulty that here everything is at magic angle. And so, because right now we have the Dirac electrons, so everything is very disorder sensitive to the environment, and also even the angle disorder. So however, in TMD, so everything is much more controlled. So in TMD, so because the effective model is described by the electron moving in the periodic potential because of the quadratic dispersion either in the gamma point or in the K point. So TMD system has like 4 different important material, MOS2 and WS2, different meta atoms and 2 different chalcogen atoms. And then by different combination, they provide 3-step complexity. The first one is the heterobilayer TMD, WSE2, WS2. And then in this system, there is, because of a large layer of set, there is no layer degree of freedom. Everything happens within 1 layer. And then in two-state homobilayer MOS2, in the valence band side, so we know because of a large bonding and antibonding, gamma pocket becomes the highest in energy in the valence band. So although right now we have the layer degrees of freedom, but the wave function is real and everything is real. So this in this layer degree of freedom can be described by a real continuum model, and we are involving 2 layers. And the third step complexity is from the two-state homobilayer homobilayer WSE2 or in the conduction band of the MOS2 because of a large spin splitting. Here the K value becomes the valence band maximum again. And then, so we have the complex wave function and the tunneling magnitude is also complex. Because of this, so the band can be topological. So the two set of Moiré band can be topological non-trivial. So, okay, regarding this three-step complexity, so there are many experiments carried on its systems. So in WSE2 and WS2, the Cornell group and the Berkeley group, they discovered a series of insulating state in a fractional commercial filling and also at the integer filling. So this remarkable insulating state also indicates that the system is somehow strong correlated. And more interestingly, they observe the kind of the magnetic transition from antiferromagnetism to weak ferromagnetism near n equal 1.2. And recently, there's a STM work from Berkeley group, Chromic group, and they find the localization of the first Moiré band at XM spot, which means that also proves that the strong localization of this system. In the second level system, in MOS2 system, they also find this incompressed mode-like state. Finally, in WSE2 and the WSE2 system, which is less studied and also more complex, they find a correlating insulating state at n equal 1 and a possible superconducting state near n equal 1, and many more are ongoing. So to understand really the correlated states in those systems, we first need to understand the non-interacting band structure and how we model this kind of system. So to start with, let's look at the building block for the Moiré bands. So how these Moiré bands are formed from the monolayer. We know there are 4 typical TMD 2D material, and they are captured. So the interesting energy scale are actually the spin orbit coupling. And we know they are in the monolayer form, they are all direct gap semiconductor at the K point. So K is the highest in the valence band and lowest in the conduction band. And the spin orbit coupling strength is very small at the conduction band side and very large at the valence band side, about like 400 milliV for WSE2. And that makes WSE2 Moiré system more special. So now let's look at the bilayer system. And then this featured band structure, as we can see, they have like a kind of similar energy in energy valence band in gamma pocket and K pocket. And in the conduction band side, there are more additional Q value involved, Q between this gamma and K, for example, in the WSE2 bilayer. And in this work, we are mainly focusing on the valence band side. So in the valence band side, there are 2 possibilities for the building block. So one is this gamma value involving from the anti-bonding orbitals, because we know that in homobilayer, bonding anti-bonding strength is very strong, and then that gives rise to this band, the bonding splitting of this anti-bonding and the bonding bands. When it is large enough, that pushes gamma value as the valence band maximum. So in these 3 combination in MOS2 and MOS2 and WSE2, the valence band maximum are at the gamma value with time Warsaw symmetry. And then, however, in the WSE2 homobilayer, because of the large spin coupling strength has been mentioned, the K value becomes the valence band maximum again. So in homobilayer WSE2, K value is the give rise to the Moiré band. Another combination from the heterobilayer, because of the valuation of this band, the bonding and anti-bonding of the large layer of state. And then the valence band of Moiré entirely comes from the 1 layer, for example, WSE2 in this combination. So again, in all these 6 heterobilayer combination, all of Moiré bands are constructed from the K value. Okay, so first, after understanding of the building block of the Moiré bands, we then need to understand the microscopic structure. So how this Moiré superlattice really looks like when at this long wavelength limit. There are two different stackings for TMD system. One is the so-called AB stacking, also referred as H stacking, which is the lateral stacking in the bulk. So in this kind of stacking, there's a large lattice reconstructions at long wavelengths, particularly because of this structure is very close to the thermodynamic stable structure. So at small tilt angle, then the lattice reconstruction becomes very serious, and we even see different structures, inhomogeneous structures with soliton domain walls, one-dimensional soliton domain walls, and the enlarged units, Moiré unit cell. The Moiré superlattice even reconstruct to a larger POC, for example, by square root 3 by square root 3. So in this system, everything is so dramatic, so inhomogeneous. So they also observe a very large Moiré potential, up to 300 millieV, because of the inhomogeneity of the Moiré superlattice. Another more interesting stacking is the A stacking, because this one is, so in this stacking, the two layers are stacked over each other. So here I use different colors for different layers. So because this is anyway not close to the thermodynamic stable structure, so the lattice reconstruction is weaker compared to the previous case. So the lattice relaxation just happens within the Moiré superlattice. So let's look at the Moiré superlattice. So here is a lattice reconstruction of a 2x2 Moiré superlattice. When we look at one, so, and as we can see, so the lattice reconstruction happens very homogeneous. So the lattice structure actually can be understood from MM region and XM region, MX region. Like MM region is the direct stacking. And then because of the close distance of the chalcogenic atom and metallic atom, the layer distance is the farthest in the MM region, as you can see. Here I plot the layer distance in the LMS2. So, and then in XM and MX, since they are related by the C2I symmetry, the layer distance are the same. So then we can roughly think that in this kind of system, because of the homogeneous Moiré superlattice structure, so everything might be understood from the electron wave function in these different regions. So as we stated before, so everything can be understood from a homogeneous Moiré potential spread out in different Moiré regions. Okay, so this is the lattice relaxation, also seen in the case of the bilayer graphene. But in heterobilayer TMD, the heterobilayer TMD, when you have a large lattice mismatch, there is a different type of lattice relaxation might emerge. So this is one example. So when you see the lattice reconstruction of the heterobilayer LMS2 and LMS2, so roughly it looks similar. So this is a plot from MX region to XM to MX. So as you can see here, still the MM region has the largest layer distance. So looks in the same manner as the homobile layer without lattice mismatch. So this can happen in a sense that they are confined by HBN substrate. This is more likely to happen. And then, as you can see, the corrugation are in a different direction. So the corrugation are, as you can see, the Z direction corrugation are along in the same direction, in a different direction. So MM region always has the farthest distance, also highest in height, and the MX and XM region are more attracted to each other. However, in a different setup, for example, in a STM setup, when you have this WSE2 and WS2 with HBN only in one side, another WSE2 side is free without any other structure. So this kind of lattice construction is kind of more natural. So they are corrugated instead of in the same direction as before. Right now, they corrugated in the they are corrugated in the same direction, not the same as before. Before they corrugated in a different direction, and they attract each other in the MX region. So this gives rise a kind of this kind of corrugation. So then the XM and MX region, they are highest in height. So when we look on top of each other, and then we actually see a honeycomb lattice. As you can think of, in a homobile layer, the highest set is at MM region. So we only see a triangular lattice of the MM region. But here in the STM image, actually we see a honeycomb lattice from the MX and the MM in terms of the layer height. So also this gives a different scenario of the Moiré potential because of a built-in electric field that will push the hole to the MM region. So the message from these two different structures is that the Moiré superlattice in STM and also in the transport in the optical experiment, they are quite different in two ways. Okay. So right now, let's understand the Heterobilayer TMD with K value without layer degrees of freedom. And if we think that the lattice relaxation happens in the same manner as the homobile layer, and this is the calculation, and then everything is more homogeneous in terms of the tooth angle. So the large tooth angle is adiabatically connected to the small tooth angle. In the STM setup, so the large tooth angle and the small tooth angle, they have so different lattice structures, as I just indicated. Okay, in the 5.7 degree, we calculate the band structure of this WSA2 and the WS2. So the band structure looks like this. And then, as we mentioned before, because of the large band offset, the charge carriers, the Hall, are within WSA2 layer. And then the effective model is described by a horse moving in a long periodic Moiré potential. So right now we have only three undetermined parameters: the effective mass and also the parameter in the Moiré potential described by the potential strength and also the Moiré phase factor phi. So later we will explain that this phi dramatically determines the landscape of the Moiré potential and give rise to different scenarios. So with this simplified continuum model, and we can see that the strength is very small, around like 15 millieV, much smaller than the AB stacking case. And the phase factor is 45. And so how this gives rise to the difference of the low energy dispersion? So, okay, if we look to the Moiré phase factor phi, then we will see that this phi, the largest difference this phi makes is the band character of the second Moiré band. So as the tight bonding limit, so we know that the first Moiré band at this region is from the s orbital of the MM region. But when phi is in 0 to 1/6 pi, the Moiré plane only has one global minimum and one local minimum. So the second band are formed from the p orbital of the MM region. But when phi is between the 1/6 pi and 1/3 pi, so the second of Moiré band is built from the s orbital of the XM region. So right now we have the two potential minimum, two local minimum. So and then we refer this MM region in this parameter region, we refer the MM as the Moiré cation and XM as the Moiré anion. So there is a very nice chemistry analog of the superatom. So this is kind of the super solid. So the tens of thousand atoms are mapped to two atoms of the cation and anion, and each cation and anion are made of many small elementary atoms. So, and also the energy scale of this super solid becomes from the EV in the usual solid to 10 millieV. So they become smooth in potential and uniform in terms of the charge density. Okay, so it turns out that in the WSC2 and the WS2 heterobilayer, the Moiré phase pack phi lies into this region. And what would this make? What kind of insulin state would this two different sites give rise? So again, let's look at the tight bonding limit. That can be easily understood in this sense because there is no topological band structure. So everything can be understood in terms of the tight bonding limit. In the WSC2 and the WS2, when you look at the 0 degree of tilt angle interpolated from the large angle, and as you can see, there are two very important energy scales. One is the Moiré band width, and one is the gap between the first and the second Moiré band. So the bandwidth is kind of small, 8 millieV here, but U is always very large. The U is around like 100 millieV. The offset repulsion is also around like 50 millieV. And that here, the first band and the second band energy difference is only like 17 millieV. So, and then when you go to like n equal 1, we would naively think that, so in the more Hubbard physics, if we manipulate everything in terms of the Molten insulator, we would think that the local gap is created by U, which is around 100 millieV. But in this system, because of the potential difference of two different regions are so much smaller than U, so the actual thing happened here is that the electrons fear to the second band, as we show in the phase diagram of the n equal 1. So at n equal 1, first there is one field host in the MM region. When U is very small, so the repulsion is not large enough, so everything fears to MM, so we have the metallic dispersion. When U becomes much larger, so and then so when the U becomes much larger, and then we develop this lower Hubbard band and up Hubbard band. And here, the U is still smaller than the potential difference of MX and between MM and MX. So we would see that the excited holes are still at the MM region. So the low up Hubbard band is still made of from the MM region. Again, when we increase U to even larger value, push this up Hubbard band higher than the MX band, then the excited state actually is formed from the MX region, which is a so-called charge transfer insulator. And we also find that the energy scale here, the thermal activity gap, or the gap from the compressibility measurement are more close to a charge transfer gap in terms of the Moiré-Hubbard gap. Okay, so that's everything we want to say in the WSC2 and the WS2 system. So after study, actually we're going to think, are there a better system for this charge transfer physics? In the WSC2 and the WS2 heterobilayer, the advantage is that charge carrier are within one layer, and remarkably, there is already an existence of the secondary minimum. But the disadvantage is that the Moiré potential is kind of weak at 10 millieV. So we always need a very long Moiré wavelength, larger than 8 nanometer, to make the strong correlated physics happen. And the parameter, especially this weak Moiré potential, are sensitive to the in-plane relaxation. So, and also it's very hard to tune the potential. So because of everything happens within one layer, it's hard to control its charge transfer gap. So can we find a system that we can really control the charge transfer gap also with a large Moiré potential? So then we discover this kind of system in the homobilayer MOS2. So this is a large angle Moire band structure at 7 degree. So in this short wavelength around just 300 millieV, we can see that the Moire band, the first Moire band, actually they are also kind of disentangled from the massive other bands. So a remarkable feature of this band structure is that there is a Dirac coin in between. So as we studied from the band structure of individual stacking spot, we find that XM region and MX region, they have the highest valence band. Because of the C2Y symmetry, the XM region and MX region, they have the same effective potential. So this protects the Dirac coin. So in order to have a charge transfer system, we need to create a potential difference between the XM and MX region. And this can be done by applying a gating field in the Z direction. So when you apply a gating field in the Z direction, that breaks the C2Y symmetry, because C2Y also reverses the Z direction. Okay, so in this system, then it's possible to create a potential difference. And then we are going to think about the continuum model involved in this system. As we mentioned before, here, because of the bonding and large bonding and anti-bonding, the valence band maximum is the gamma valley. So in this gamma valley system, the effect model, so as we can remember, in the heterobilayer, this is only one pieces, the potential with the kinetic energy. Here, because in the because we are in the homobilayer, there's additional the tunneling magnitude between the two layers. So the tunneling, the position dependent tunneling also involves, and then we write down this 2x2 continuum model. So in this 2x2 continuum model, so very different thing from the K-valley homobilayer is that so everything is real because we have a time also symmetry at gamma. So the continuum model wave function should be real. So the tunneling magnitude is also real, can be written in terms of the 3 Fourier harmonics. So because here the Moire, effective Moire potential actually are derived from both the here the intralayer potential part and also the interlayer tunneling part. So the Moire potential is kind of more stable in terms of the tooth angle. So this system, we see more kind of uniform angle dependence. So as you can see, this is the bandwidth with is extrapolated from the DFT and from the continuum model with the same set of the parameter. In DFT band structure, as you can see, this follows very nicely with the continuum model. So we can see that really one set of parameter can describe really the angle dependent. So in this system, so and at different tooth, even at a large tooth angle, you already expect a strong correlated physics can happen. So right now, yeah, let's look at the a long wavelength system, for example, at like 2.86. So as we mentioned, we aim to have like a create a potential difference between the two Moire regions. And from DFT, actually, from the real DFT, when we apply 0.5 watt over nanometer, we already create like a 3 to 5 millieV charge transfer gap. And then when we further reduce the tooth angle in the long wavelength limit, actually we can see that the 0.2 watt over nanometer electric gating field can push all the charge of the first band to MX region. So they are fully separate in a sense. So we create a fully charge transfer system in the MOS2 at 2 degree. Okay, so then with this tunable charge transfer energy, so what can we achieve? A natural thing we can achieve is this tunable charge order. As I mentioned, in a heterobilayer TMD, So the charge order has been discovered in a series of fractional fillings, but it's not so because of potential is not tunable. So the charge order at every fraction they are retained in the same state. However, in the honeycomb lattice, right now, when we simulate, introduce this potential difference here in the B region. When we so previously in the heterobilayer, so everything is just with the Coulomb energy. But right now, when we induce the potential difference, as we can see, the change of the potential difference can push the kind of insulating state. For example, this is the insulating state at 1/2 in the heterobilayer TMD. But when the potential difference go to 0, we have the sublattice balanced charge order. And also in the 2/3, so they can transfer from this enlarged honeycomb lattice to this stripe-like charge order, breaking the rotational symmetry. So just by tuning the gating field, we can tune the energy difference. We can tune the different charge order. Okay, and then because right now the charge order is tunable. The charge order is tunable at least at n less than 1. When we look at different scenarios at n larger than 1, there are even more kind of possibilities in terms of the excited state. So for example, for n larger than 1, when we add 2 holes to the whole lattice, there are different scenarios. We can add them to just B region, forming this dipole, and we can add this to B forming this hole, and then also there are electric polaron. More interesting, we have this trimer that the 2 field holes field to 3 B sublattice, and then create an empty site at the AA region. So this bonding charge 2e trimers create a charge 2e object. So we create a kind of electron pairs, electron 2e pairs from the repulsion. And the bonding energy of its trimer is given as by the potential difference and also the offsite interactions. So this system in the MOS2, we achieve a tunable charge transfer energy. So it's able to engineer to make the bonding energy of its trimer to positive. That means when data is large enough, the epsilon B can be positive. So the charge to each trimer can be less in energy. So we form this charge to can be the smallest, lowest energy excitations than the individual holes. And then the possible material platforms, as we mentioned, can be either this MOS2 and also MOSE2 with HBN in between to suppress the tunneling. Okay, so the first summary is that the first part that we can understand the TMD Moiré splice with 1,000 to 10,000 atoms in terms of the diatomic crystal, and they can form in this metal charge transfer insulator and a mortar insulator and many different kind of insulators because of the localized one-year functions at the stacking region. And the second message is that we can engineer this charge transfer at the Moiré scale around like 10 nanometer. So previously, so when we talk about the charge transfer insulator, they are always within nearby atoms within astron scales. But here, actually, charge transfer can occur even at like 10 nanometer. Okay, and finally, we propose the two-level system, WSC2 and MOS2, as an ideal platform for the charge transfer insulator and also unconventional charge order because of the tunability of the potential difference in this honeycomb lattice. Okay, so right now let's go to the second part of this talk. So more on the kind of magnetic property. So as we know, when we compute the no energy dispersion of the TPG or in the TMD, the computation cost is insane. For example, the first study of the TPG in terms of the full ab initio calculation is carried on in the K computer in the largest cluster in Japan. So they calculate 10,000 atoms, and then it takes almost like 500,000 cores running for several days to compute the lattice relaxation. In the Tuesday MOS2 with 6 nanometer wavelengths and around like 2,000 atoms, the computational cost is on like, we use like 4,000 cores with 16 terabyte memory for 3 days. And for even larger wavelengths, the calculation became, so this is, because this is complicated for physics, we only calculate the band structure without spin coupling. If we want to include spin coupling, and this is unaffordable kind of computational cost. And then we began to think, can we develop a specific Moiré density functional theory for the Moiré system? Because although right now we have like 10 to 6 electrons in the Moiré superlattice, the interesting electrons actually is the very few Moiré electrons, the Moiré valence band and Moiré convection band near the Fermi level. So the interesting band is actually less than 5. So we only need the information of these very few Moiré electrons. Do we really need to compute the 10 to 6 electrons in the superlattice? So this is the motivation that then we are going to think about, can we replace the 3 singular column potential from the tens of thousand atoms by this 2D slow varying Moiré potential? As I mentioned before, when the Moiré space is homogeneous, so everything is slow varying, structure is slow varying, and also the Moiré potential is slow varying. So this gives the possibility to replace the singular column potential to Moiré potential. So then now we can apply the continuum density function theory to the above continuum Moiré potential by replacing the previous one to the 2D potential, and we apply the same scenario. So in the density functional theory, the crucial thing is that we map the collision energy of the electron to the exchange energy and the collision energy of the electron to the exchange functional. The simplest one is the local spin density functional approximation, which approximate the exchange energy just in terms of the electron density. So one remarkable note is that the DFT actually is an exact method in one limit, in the homogeneous limit, when the electron density is uniform in the whole studied region. And this LSDA actually is exact for the homogeneous electron gas. When the V0 go to 0, so the DFT is exact. However, so when this V0 is non-zero, so the DFT also gives to a very good approximation, at least better in a 3-dimensional case. We know in the 3-dimensional case, the charge is dramatically inhomogeneous. They just distribute on an astron scale around an atom. But here, as we can see before, the charge density actually is spread in the nanometer level. Okay, the thing that we get out from the Moiré density function theory in the WSC2 and WS2 system is about the filling-dependent magnetic ground state. So the DFT is particularly good for the magnetic properties in this itinerant system. As we know, for n less than 1, so there is a series of insulating states. So everything is very singular and very strongly localized. At n larger than 1, when we fill to the second band, actually the Maillard susceptibility, the resistivity tells us this is more metallic-like. So in the metallic region, when we calculate the energy of the 3 different states, the long-polarized state and the ferromagnetic state and the SCAW state, actually we see a transition. The long-polarized state is always highest in energy. indicating that we are so here even we are in the metallic region, so the electrons are still correlated. So at 1.2, we see a crossover that the FM, the ferromagnetic state, becomes lowest in energy. So that means that at n equal 1.2 to 1.3, we see a transition from the antiferromagnetic order to the ferromagnetic order. So, and then this is the result from the numerical Moiré DFT. So do we have a simple understanding for the ferromagnetism in this narrowband system? So if we understand everything in terms of the Hubbard model, the doped Hubbard model, so we know that the magnetic ground state is still antiferromagnetic. So why we have this ferromagnetic ground state or ground state? So then let's go back. So in this homogeneous, more itinerant system, let's go back to the ferromagnetism in the two-dimensional electron gas at a zero potential limit. Actually, we can see when the RS is larger enough, like 25, or when the density is low enough, RS is the coupling constant, inverse proportional to the electron density. When the density is low enough, actually we can see the ferromagnetic liquid state is lowest in energy than the unpolarized state. So this gives rise to a ferromagnetism in a two-dimensional electron gas. So did we see something similar as in two-dimensional electron gas? So, and then the answer is yes. So when we use the Moiré DFT to calculate the itinerant ferromagnetism, especially energy difference of the polarized state to the non-polarized state, we can see that the energy in the beginning has zero potential limit. The non-polarized state has lowest energy because here the RS is around line, so density is not low enough. However, when we enlarge the potential, actually we can see the energy is adiabatically connected to the large potential region. And we can see, so the susceptibility here is the third order susceptibility is much larger in the case of the polarized state. So eventually, the energy of the polarized state becomes smaller than the non-polarized state. And then that gives rise to a polarized ferromagnetic order, as we can see from here. So when we go to n equal 1.3, the fully polarized state actually is the lowest in energy. Okay, and then we believe this is adiabatically connected to the case of the two-dimensional electron gas. And the electron gas moving in a purely potential picture is really valid when we in the metallic region of the correlated Moiré states. Okay, so this is also the comparison with the experiment. Experimentally, they plot the G factor with different fillings, and then they also see a weak transition. They see a transition from antiferromagnetic order to a weak ferromagnetic exchange at n equal 1.2. So, and to conclude, this metallic ferromagnetism is surely beyond the single band Hubbard model. Okay, let's again to have like one insight of the Moiré DFT. So the good thing is that the Moiré DFT could predict the magnetic properties in the metallic region. And when we let's recall the Moiré potential phase phi also stands for the potential difference. So when we tune the potential difference of the two Moiré regions, the magnetic ground state is also varying from the SDW case to the ferromagnetic state case. So at a confined filling, if we keep the filling factor just by tuning the gating field, actually we can already achieve a tunability of the exchange parameter from SDW-like to ferromagnetic-like. So that achieve a tunable Moiré magnetism by gating field. Okay, so this brings me to the summary of the second part. So the physics of the correlated Moiré system actually is governed by the low energy electrons. So which we need to look into. So, and this is ideal situation for the DFT. So even better in the 3-dimensional case with really inhomogeneous atomic-like charge distribution. So this provides an ideal situation for the development of the DFT. And we apply the DFT to the system with weak potential and predict the itinerant spin value ferromagnetism. So, and then we attribute this spin value ferromagnetism to the interplay of the Moire potential and the Coulomb interaction. So yeah, that's all for this talk. Yeah, thank you very much for the attention.
Yeah, so thank you, Yang, for this very great talk and this very nice work. I'm Chung from Boston College, and I will help Liang to host the Q&A session. So if you have questions, please raise up your hand. Okay, so Brian. Talk. Brian, can you say? Can you speak?
Let's see, the way that we're set up, I think if there's questions that somebody should type up because nobody can speak.
Okay,
sorry.
Sure.
And so they should put them in either the chat or the Q&A. And then if you could read the questions.
Okay, got it. Yeah. So Brian, could you please type your question in the chat box and I will read it. Okay, meanwhile, I think Yang, I have a question. So can you go back to your first session? Your first section. So you mentioned something like so the transport measurement and the STM measurement are different in 2 ways. I think I missed your points there. Can you repeat? What 2 ways?
Yeah, sure. So the main difference is the corrugation direction. So although we know that the layer distance of MM region is always largest, but then they can corrugate it in the different direction. I mean, in this way, and then still the MM region are the highest in height. So if we look in the Z direction, so this is the MM region we start from. So this is the line plot from MM to XM2. So as you can see, and then, but so this is the lattice structure when we have 2 HPN at both sides. So that pushes, so and then they are corrugated in the different direction, as you can see. I mean, the corrugation direction of the MX and XM. So, but yeah, maybe we can have also a look on this one. So in the STM setup, however, you can see that although MM is the highest, but MX and here MX, XM and XM, they are corrugated in the same direction because there is no HPN on top of this lattice. So at small wavelengths, because of the lattice mismatch, they tend to corrugate it in the same direction.
Okay, so basically, you meant that in transport measurement, we have the HPN on top, but in STM, we do not have.
Yeah. In STM measurement, we have only HPN at one side, at the WSE2 side. So there's no HPN at the WSE2 side because we need to put the tip there. So yeah. So that makes the lattice structure dramatically different. So this is also seen in the sense of the, as you can see, the STM image. When you see the STM image, so if we are in the previous case, so we are corrugating in a different direction, the highest in height would always be the MM region. So we would have like a triangular lattice, as you can see from here. So this is a triangular lattice. But here, actually, this is a honeycomb lattice. So that means that MX and XM region, they are highest in terms of the height. So when we probe the tip, and so this, then the structure here is dramatically different. Also, this lattice structure can happen only when you have one HBN at one side. And also, so even, but when you're at like large angle, for example, at 5 degrees, so this is still not the lowest energy. The lowest energy lattice relaxation is still like this corrugation in different direction. So yeah, so to conclude, the STM setup can only happen at very long wavelength limit and with only one HBN at one side.
Okay.
So, yeah.
Yeah, I got you. So I don't see the question.
Well, there's a question from Brian Girardeau in the Q&A.
In the Q&A.
Yeah.
So
I can read
sorry,
it if you want.
Okay. I saw it. Sorry.
Okay.
Yeah. So yeah. So the question from Brian is, if I understand it correctly, you can show that the Wigner crystal states exist due to the charge transfer exciton state between the MM and the MX sites. Wouldn't that mean that there is no strong correlation in these systems and that Wigner crystallization is only an effect of those charge transfer states? And to make things clear, I'm a student from Brian sorry to pronounce it wrong. My name is Maximilian Kogo. I'm sorry for that. Yeah.
Okay. Yeah. To answer this, so yeah, for the Wigner crystal, actually this is always strong correlated. So I would say that here we need a strong correlation to form the generalized Wigner crystal. Although we have a potential difference, so but the U and the V are always there. So that makes, I mean, the parent state, so to say, the generalized Wigner crystal is already constructed from the strong correlation of the U and the V. So otherwise, we wouldn't have this kind of insulating, very insulating state. And then the charge transfer here just affect the excited state. So I think, yeah, that maybe answer the question. So the strong correlation is always there. So that gives us the parent generalized Wigner crystal state.
Brian, does that answer your question? You can type yes or yes, thank you. Okay. So do we have more questions from the audience? Okay, I actually have another question, Yang. So you mentioned the charge transfer band structure. Are you saying that before and after the charge transfer, the band structure is renormalized in some way?
Yes, the band structure will always be renormalized. So, so before the transfer, I mean, before the charge transfer, so if we are saying somehow before the charge transfer is n less than 1, so the band would be extremely flat, because so when we have less than 1 host in the system, the correlation, the U is much larger. So, but in the charge transfer scenario, the bandwidth is much larger. So.
I see. So you first calculate the single particle band structure, and then you identify the Moiré sites associated with the bands, and then you fill in 1 electron per site, and then incorporate the correlation and reconstruct the bands.
Right. Yeah. So here all the band structure are non-interacting network. So we first need to have the non-interacting Hamiltonian, and then consider the effect of the interaction.
Okay, I see. So, okay, I don't see more questions from the Q&A panel. So if we do not have more questions, I guess we'll thank the speaker, Yang, again. for the very nice talk. And thank you all for coming to this talk.
Okay, thank you so much. Yeah.
Yes, thank you so much.
Thank you. Bye.
Bye.
Bye.